Yeah, so maybe we'll do that, but let's see if we should wait or not. No, let's just continue. So what you're talking about is finite fields, right? We should look at finite fields. Okay. So
एंड इसी का पहला वाला प्रूफ था कि कोई भी फाइनाइट फील्ड का एलिमेंट नंबर p टू द पावर n होगा.
yeah, that you know, so then that's very good. Okay, but now we are going to prove the converse. है ना कि तुम कोई भी फाइनाइट कोई भी p टू द पावर n लो, सो एक फाइनाइट फील्ड होगा इसका कार्डिनैलिटी p टू द पावर n हो, right? That is what we are trying to show, and then what you are asking will be done. But even after that, let's do it. But then you should specialize to those cases and actually construct the fields. I'm sorry, I do not completely remember, but field with p to the power n elements. So what you have to do, I think you start with fp, which you know exists. This is a field which we concretely know. Sorry. So this you have, and this is just one of the ways. There would be, I would want to know other more interesting ways, but since I have to tell you quickly, so I'm just going to tell you the way I know, but I would be interested in knowing other ways. This is a classical way, I think. And what is the way? It is just take take this polynomial, okay? And if you think a little bit, you will see that it's not a surprise to consider this polynomial. If you know Fermat's little theorem, then you know that this is not at all a surprise. Why we are taking this? Think about this. Take this polynomial in this ring Fp. Okay. Okay. Now from field theory, you know that this polynomial has a splitting field. Right? It has a splitting field. So what is that? So there exists, this is from general theory. It's not difficult, but we'll not prove that right now. There exists a splitting field. I will define what is splitting field if you know it's good. Splitting field just means that you are looking for the smallest field where all the roots of this are available. Roughly, it is that. Okay. So you are looking for a field extension. You're looking for a field that contains Fp such that in that field, this polynomial, because this polynomial can be seen in that polynomial ring in that, and there this polynomial completely splits into linear factors. Take the smallest such field, it is called the splitting field. There is a lot of theory, there is a lot of interesting abstract theory, and in fact this is one of the parts that goes into the definition of a Galois extension, that it should be a normal extension. That's also what it is called. But roughly, as I said, you remember that for the time being. So just take the splitting field. Why I'm using there is a reason, but yeah, the splitting field, because you can show they are all unique up to an isomorphism in a very strong sense, but Also not in a, but anyways, yeah, it's, I don't remember it. I have to, when I write, then I can remember, but yeah, right. Splitting field of this, okay, say FQ, right? So what is the size of FQ? Size of FQ, yeah, I do not know. What will it be? That's what we are interested in. We want to show that size of FQ is P to the power N. That will do the job, right? Okay. So first you have a theory which is comes before this, where this splitting field existence is proved. Okay. And there you don't have finite field, so it's easier to prove. It's a clean setting. You prove it in the general Bose setting, so just very clean, and then you use it here. Then the claim is, it's not difficult to show. Claim is that size of FQ is P to the power N. And in fact, this is not a good claim. The better claim is that the roots of x to the P to the power N minus x form a field. This you can just prove easily. And the roots themselves form a field. Right? Because you know all those identities, right? That if you take, if alpha is a root and beta is a root, you want to say this is also a root. Okay. But then you know that this is zero. Well, this is just a Fermat's thing, right? That this I think we just used in the last class, right? We used this in the last class. What did we use? We said that if you take uh, if you take that is not true. But I mean, yeah, just simply, yeah, what I'm just trying to say is simply this, that this is equal to this. This first you can see. Why is this equal? Because this FQ, the characteristic of FQ will be P. That is because it's an extension, right? The one is the same. One in FQ same as one in F. One in FP same as one in FQ. Same. So because of characteristic reasons, this will be true. And so this will be true just in by induction. Right? You take P square, P back. So if sum of the roots is root, you show product of roots is root, blah, 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 you just do it. So it forms a field. So what does it mean? Well, it then it means that this FQ is basically roots of because no, by definition of smallest, it's this FQ is just this itself, right? And then this is equal to and now so the size this implies that the size is P to the power N. Sorry. This implies that the size is P to the power N. Here you have to just check. You have to show the roots are distinct. That I will not do. You just do it later, right? You just can check it and maybe roots of x are distinct. Okay, try to show this, and then it's done. You have your field. This also I can do, but it's not today. Yeah, but you would want to maybe if you want to see an example. Finite fields are a huge topic, and so if you think like field with 8 elements, right? Sorry, what is yeah, 8 something, and that is a little bit okay. Field with 8 elements. I just do it. I mean, I have told you what it is. Maybe here there is a further fact which you should prove. is that this FQ cross, this is a group, is a cyclic group. Okay, cyclic group. Okay, so if you uh, assume this, that it's a cyclic group, then can we concretely write down the field with 8 elements? Like what are all the relations and everything, right? You would want to write that. So if it's a cyclic group, then you know that there is a generator. That's called a primitive root of, yeah, alpha square, alpha cube, 6, 7. Yeah, this is the field. But this won't fetch, this doesn't fetch much other insight, right? This tells you the multiplicative structure. I'm sorry, yeah, this is not correct. It is quite nonsense. This one cyclic group with 7 elements, and of course we have our 0. It becomes a cyclic group, but the number of elements is p to the power n minus 1, right? Yeah. 0 is not in the cyclic group, of course, under multiplication. So this is the field with 8 elements, but this doesn't say much. You need to say you need to say the addition. So please tell what should the addition be. It is not difficult because you know that you know what is going on, right? You just have to take this x to the power 8 minus x equal to 0, and you have to factorize this over f2. You can do that. I'm not going to do it. Factorize over f2, and then you will find a factor with degree 3. Correct? There will be a factor with degree 3, and it will be irreducible. Okay, and that factor will with degree 3. Okay, if you take a root of that alpha, if you call a root of that to be, let's say, beta, if beta is a root of that, then what can you say? That the degree of the extension is 8, is the degree of the extension of that beta of f2 adjoint beta will be what? It's contained in f8, right? That's by definition, right? F8 is the roots of this. The degree of this is what? Is equal to 3, correct? Just 3-dimensional vector space over f2. And what will be the size? It will be 8, 2 times 2 times 2. So this will be an equality. Okay, so this is this is sorry, yeah, this is the thing. This is the guy, right? I mean, this is the element, right? This is your alpha. Why? Because this generates f8, and so if you take the powers of beta, you shall get everything in f8. I mean, yeah, or no, wait, I'm sorry. So no. So what I'm trying to do is I'm trying to now understand the relations between these alphas, right? I'm trying to understand the relations between these alphas. What is alpha? Alpha is something for which alpha to the power 7 is equal to 1, and 7 is the smallest. Okay, well, 7 happens to be a prime here, so it's smallest by definition. But yeah, that's the problem. I'm not saying it properly. So to say it properly, I should say like this, that you have this, and order of alpha is 7. That's the smallest power. Okay. Now our job is to find the relations between the elements of alpha, between this alpha. That will be the thing to do. So any suggestions? You see that these are not linearly independent. I'm not saying that it cannot be. Okay, but these are different because the order is 7. It should be this beta only, but I am unable to prove it. This beta, which is the root of the minimal polynomial, which is the root of irreducible polynomial of degree 3, that should be the thing. Um, that's the missing bit. So you see why we are doing that. Okay, to get the relations. Otherwise, we don't understand the additive structure then of on this field. Right? We want to show this cannot happen. Yeah. If this happens, right, then this implies that beta to the you see this contains the multiplicative group generated by beta. That's clear. That's obvious because that's the field generated. So it is like this. So see, I mean, if there is any beta which works, it has to be this kind of beta. Any lower degree polynomial ka beta, a beta of some lower degree polynomial is not going to work because it will fail at this level itself. So because we are saying that this beta cross is equal to f8 cross. That's what we are saying. So any other beta will not work. And then you know that there is a beta which works, right? And so it has to be beta of this only. Okay. And then it's like if you have two betas, two roots, then that is, yeah, there is some proofs to be done that a group goes to a group and some things, field isomorphisms. But yeah, if you assume those things and then it's true. Yeah, this is cyclic group also I'm already using. So then it is true. Otherwise, it's not so clear, because you see beta to the power. Let's take an example. Right? So if beta to the power 4 is equal to 1, how do you get a contradiction? Right? You get like beta to the power 5 is beta, but you will want something like beta to the 2 to the power something equal to beta, right? If you have that, so if what I'm saying is that this beta satisfies this, right? But this beta cannot satisfy something like this, right? Otherwise, like the minimal polynomial degree, what will happen to it? It will become lam. Then the beta minimal polynomial over f2 is this, so it cannot. Right? So you understand what's going on, right? So it's not possible. So for beta to satisfy a lower degree thing like this, but I want to prove it doesn't satisfy a lower thing like this, and that I am not able to do directly. So that's why I'm appealing to these general facts. Okay, and what are the general facts that you see that you take because nothing else works other than root of this kind of minimal polynomial whose degree is 3, which is the power of 2 there. So this will work. Then nothing else works. Something works from the theorem that the multiplicative proof of a finite field is cyclic. Okay, and that's a special case of, but so something works. Now, so that is one of the roots which works, and I'm saying that if one of the roots it works, then for every other root it works. Okay, and that is because again that's the theorem. So if you take the minimal polynomial, if you exchange the roots, it gives you a field automorphism, and that takes the group to group, and order it remains as you can do. So, but then the upshot of all this is that now the exercise is that here you can just calculate and show that no other. Let's do case work. Let's check, right? You can just do it. But what you should do is factorize this completely over f2. Find that factor of degree 3. Okay, write it down. It will be something. Write it down, and that will give you the relation. That's your alpha, and then you will know that alpha will be something like, I don't know. This factorizes, so forget it. But there will be one something degree 3, whatever, right? Whatever. So that will give you a factorization. So that will give you a relation, and that relation you use to do the arithmetic in f8, right? That relation will be useful, right? So, yeah. That will give you a description of f8. So like this. Describing the relations, I don't think it's easy in a finite. I don't know actually. I don't know anything about finite fields. I just know it's Galois extension. You have some algebraic closure, some things. Yeah, I'm not an expert in finite fields. Yeah. But I would like to know. If you can tell me something interesting constructions of finite fields. Yeah. But probably already I've given work, so you can explore this topic later. But yeah, I have some things to say, but I will not say right now. It's late. So that's.
And we need to define the additive and multiplicative operations on this field, right?
So multiplicative operation I've already defined.
But addition.
For that, I'm telling you now, you factorize. That's what I told, that you factorize this f2, and you will get the additive structure. Factorize this over f2. Look at the polynomial of degree 3, minimal polynomial of degree 3. That will give you some relation, right? Something, I don't know. You have to factorize and check.
Yeah.
And that relation equal to 0, that will dictate the additive structure, no? Like when you add, what happens? Something becomes a relation. That will generate the relations. Okay? It's a mysterious thing, man. Finite fields is a very strange thing. Yeah, one can say it in very nice ways. If you know structure theorem of abelian groups, finite generated abelian groups, it's because it's an abelian group, and one of the things that is there, right? Like you could look at this, right? I mean, no element has additive order more than 2. Okay, so it means that it's like if you look at the structure theorem, if you look at it as an abelian group in a structure theorem, you will only have, I mean, just correct me if this is wrong. I mean, you will only have like Z copies of Z2, right? Is that correct, Vaishnavi? You will only have copies of Z2 if you apply the structure theorem, looking at it as a group under addition, because it has no element of order 4. Every element has order 2, additive order, I'm saying, because characteristic is 2. So you have this abelian group, which is like so simple, but you want to put a multiplicative structure on it also. And the claim is that it's a unique multiplicative structure, man. That's awesome. I mean, that's like something deep, right? That there is only one multiplicative structure you can put. You can show that this field is unique. There is no other field of order 8. And that follows again from some general theory of splitting fields, that there is a unique splitting field. I said so that applies. So that's like a very, and that goes into some very nice theories. Like you have a ring and addition. For example, I mean, you just ask yourself, right? You take the integers and you just forget the multiplicative structure, only look at the additive structure. Now think, can I put some other multiplicative structure on it in a reasonable way? And maybe you'll find that you cannot. Just check it. And this is some very deep things, like, yeah, we have an additive structure, but now when you want to put the multiplicative structure, you get a unique, cannot put too many. And that shows like there is some relation between addition and multiplication, which we don't understand, right? There are so many, like the conjectures, like if you look at the ABC conjecture, you should just read about these things, right? ABC conjecture. You should read about it. And it's obviously, I think it's unsolved. There is a proof, but I don't know if people have agreed on that. Yeah. This we look at, that really tells you that we don't understand the relation between addition and multiplication. Yeah, you should. But you should please tell me, someone should tell me how to construct finite fields in other ways. There are some combinatorial ways, awesome combinatorial ways, which I don't remember or I have not studied. Uh, some things I knew, but you should tell me. Okay. Yeah. All right. So let's stop here. I will stop here. So meet next. I will let you know. Maybe Saturdays. Oh, okay. Right. But I'll mail you. Right now I have to go. So I'll talk to you later. Okay. Right. It's a lot of interesting maths to do. Explore it. Okay.